All right, we are live on our Wednesday HVAC School live stream. Really excited about the topic and our guests today. Today we have Ross Trethewey. Ross is, well known for being on This Old House. He's kind of a big deal, but also his engineering firm TE2 Engineering. Russ King is the CEO of Coded Energy and Quick Model 3D. If any of you have had a chance to use the really awesome software where you can play a video game and design a duct system. So that's Russ's company. And we were gonna have Alex Meany, and he's actually like at 10, 15 miles away from me right now. And he was like, can we do it together? I'm like, I don't think you want to do it in this office with me. So he wasn't able to make it just because his internet at his hotel isn't good enough to do it. So we miss Alex, but I'm sure we'll get him on soon. And we're going to talk about equipment selection for cold climate heat pumps. We're going to talk a little bit about the load calculation side of things and some of the things to watch out for, some of the manual S stuff, all that kind of stuff. But then just a lot of practical stuff. What to pay attention to when you're working with cold climate heat pumps. So to start with, I just want to do a very open question just to get the conversation rolling. I'll start with you, Russ. What are some of the things that you're seeing out there? Some of the things that are kind of the obvious successes, but also some of the obvious failures as it relates to cold climate heat pumps.
Sure. I think the general problem that I'm seeing a lot of is contractors simply not doing load calculations and winging it. That's a huge problem. I mean, if you don't even know where the target is, how can you shoot at it, right? And I'm seeing a lot of that. They're using the size of the furnace that they're replacing as the basis for sizing the heat pump. And we all know that if there's AC in there, the furnace was sized for airflow. It wasn't sized to the heating load. And so they're off to a very bad start there. So I'm seeing a lot of that. I'm seeing a lot of contractors still afraid of heat pumps. And I live out in California. To be perfectly honest, I don't have a whole lot of experience with cold climate heat pumps, but I do have a lot of experience with the new Manual S, which does address those and takes those into account. And I'm seeing a lot of HVAC contractors trying to talk homeowners out of installing heat pumps. And we're not in a bad climate. Like the Bay Area, the San Francisco Bay Area, which is a huge megalopolis, is like the perfect climate for heat pumps. It's like the perfect climate. And still contractors are like, no, are you sure you want a heat pump? I don't know. They blow cold air, and I've had bad luck with them and all this other stuff. So that's what I'm seeing. I don't have a whole lot of experience with the specific equipment that people are installing. I've looked at some of the Mitsubishi stuff and all this other stuff, but it's just kind of the general, is the industry ready for something like this, is the main problems that I'm seeing right now.
Yeah, good stuff. Ross, how about you?
Yeah, I mean, we're seeing successes and we're seeing some pretty bad failures, so it's kind of all across the gamut there. On the success side, I think there's a lot of, contractors that are kind of really buying into the technology and getting trained on it, doing a load calc, and kind of doing it right, from the start. And those are obviously the success stories, proper design, proper application, and a lot of that happens to be on the new construction side, where I think the guys don't have the kind of the they're thinking about, hey, these older houses, they might be a little bit harder to actually apply with heat pumps. And so some of the failures that we've seen are exactly that: misdesign and misapplication. A lot of times it might be an older house, a lot of air infiltration, poorly insulated. They went to a class one time, they heard that these cold climate heat pumps work, they install it, and maybe it's way too much heat pump capacity. Maybe it's not enough heat pump capacity, and the system struggles. It goes into defrost. We've got issues. Nobody's happy. Homeowners not happy. The HVAC contractors not making returning phone calls, and so there's challenges there for sure. And so we're in a perfect climate for heat pumps that in the New England market, it's a very tough market to actually get right with heat pumps. We've got heating loads that are 2 times our cooling loads in many houses, and on top of that, we also have really low ambient conditions. If you're talking about Maine, you're talking about negative temperatures. And in Massachusetts, we're in single digits. For design criteria. So heat pumps obviously struggle as the temperatures get colder out. So you just got to take that into account. So not to say you can't do heat pumps, obviously, to fully electrified buildings. We do that all the time, but it's harder when it's an 1860s house, installed in New Brunswick or in Maine. That's a harder, uphill battle, and a lot of times it comes with performance assessments and usually a different package, right? Not just the heat pump.
Yeah. Go ahead,
Can
Matt.
I speak to that? So I live in Dallas, and my house was built in the 1930s, and I put in a heat pump. Went from a gas furnace to a heat pump, and it's a like a low ambient heat pump, and I did that probably 3-4 years ago, and very quickly realized that I knew nothing about load calculations, because I realized my heating load was even here in Dallas much higher than my cooling load. The first winter, I did a lot of silly things. I put it right on the ground. The defrost started backing up the back of the unit. I was out there with a shovel, chiseling ice off the back of my heat pump, which I do not recommend. But I mean, that's also a good place to start, is maybe your own home, because at least if you have to fix something, it's close by.
Yeah, kind of to that point, it's a lot of times those of us who talk about this stuff a lot, we assume that the solutions are in these sort of finer details. And I'll quote you here, Russ. We often are splitting hairs when we should be shaving heads. I think that was your quote. And kind of to your point, you got to start by people just understanding a load calculation in the first place. It's more important than it was, right? When you can have massively oversized gas furnaces, and really there's minimal impact when you have a massively oversized gas furnace compared to having a heat pump where you're attempting to do both the heating and cooling with one appliance, essentially. And so you really got to get that right. And to what Matt's saying, it's amazing how many HVAC technicians and contractors don't recognize that even in markets like Central Florida, our heating load is still greater than our cooling load, right? When you're talking about peak, regardless of whether you're looking at a design day or not, but you certainly have moments where your heating load is greater, because you just look at the delta between your desired indoor temperature and your minimum outdoor temperature is always going to be much greater. And again, when I say always, obviously there are markets that's not true, but even in Central Florida, we will have a 25-degree day on occasion. And we still have a desired indoor temperature in the mid to high 60s, which is a significant delta. So it's these kind of basic concepts that I think we have to drive home first and foremost. One thing that you mentioned, Ross, that I think is really, really key about your market is not only do you have high heating loads that are significantly higher than your cooling loads, but you also have a market that still has latent. Right. When you have a sensible only market, you can get away with a lot of stuff. But when you have a latent market, getting that cooling size properly is really important so that you don't have issues on that side.
Exactly right. Yeah. We got all four to deal with. We got to humidify buildings in the wintertime. We got the dry air, right? We have to obviously provide cold climate heat pumps to heat the buildings. But we also need to cool. We also need to deal with latent loads and dehumidification. So we've got the full Monty in terms of hitting all four. So a lot of our high performance builds, we're going to have a cold climate heat pump to do heating and cooling. We're also going to have a ducted dehumidifier to handle the latent loads. And a lot of times we're going to have a steam humidifier to add moisture to these buildings. So, it's, it adds to the cost, and adds complexity, of course, but we're just not in a great climate, for dealing with this. I wish we lived in Phoenix, from a climate perspective, but we don't, and so yeah, we definitely have some extra challenges there. And, the tricky part with these is that when you're sizing for heating, of course, you're oversized for cooling, to your point, Brian. When you're dealing with, these late loads, we have a high performance heat pump. It's oversized for our cooling loads. And on top of that, because of, CO2 and different regulations and standards, they're getting higher and higher in terms of sensible heat ratios. So now what used to dehumidify pretty well with the 60-40 split, sensible heat ratio of 60, 0.6 to 0.6 sensible, 0.4 latent. Now that's switching to 0.9, 90% sensible heat ratios or above in some cases. So they're basically sensible cooling units only. They don't handle the moisture load. So we get a double whammy there. Oversized for the cooling load, and on top of that, not being able to extract as much moisture as they used to.
Yeah, and that's often not what, again, when you just listen to the boilerplate marketing, like these are amazing dehumidifying units and they heat really well and all that. And it's like, you got to look a little bit more carefully. You got to look at the expanded performance data that was one of the big takeaways. I just got back from a passive house conference in Seattle, and one of the big takeaways I took away was like really paying attention to the performance specs of a lot of these variable capacity and multi-stage pieces of equipment, that they don't all perform the same. I mean, and I've known this for a long time on the latent side, because that's what I'm always thinking about, removing moisture in my market. But even in the cold climate side, you'll run into some pieces of equipment that the tonnage is the same, and they're both technically what you would call high heat or, you know, low ambient type heat pumps, but they don't perform the same. You'll have some that actually produce at higher than the nominal tonnage, even all the way down to things like minus 5 degrees. And you'll have others where there's a steep drop off, even though they're still considered to be, you know, low ambient heat pumps. So it's really important to dig into that expanded performance data and pay attention to that.
That's right.
Yeah.
That's right. Yep.
I think one thing off of that, and then a question over to Russ. I think I mean, basically you're going to typically sell one line of equipment. So once you kind of figure that out, like it's a lot of work up front. But once you kind of know what your options are as a contractor, you know, you're pretty much picking between three or four different units. And then Russ, this does tie into the new Manual S. Is that correct?
Yeah, I wanted to bring that up. I wanted Russ to just kind of riff on this a little bit of kind of what we're seeing in the new Manual S and what to pay attention to there.
Yeah, there's actually like 9 different options for sizing heat pumps. You've got the 3 main ones up there, but there's a lot of nuances now in the new Manual S, and in a lot of ways it's a lot more flexible. But with flexibility comes complexity, and you know it's not as simple as the old Manual S. There's 2 sort of schools of thought to sizing a heat pump. Is you size the heat pump to the cooling load, and then if there's not enough heat, you make up the difference with strips. That's the old way to do it, right? And then there's a lot of places like California, for example, where they're super energy conscious, is they're trying to mandate sizing the heat pump to the heating load, and then whatever happens to the cooling load happens to the cooling load. Well, I've been preaching not to oversize air conditioners for I don't know how many, 25 years probably, that oversizing air conditioners is a bad thing. And now we're basically saying, well, you don't have any choice. You have to oversize air conditioning. In some cases, I mean, Manual S will allow you like up to 30% in some cases. And then in other cases, there kind of is no limit for the air conditioning sizing, but you have to have variable speed capacity that can throttle down. And you have to have good duct design. When you start messing with the airflow, when you start screwing with the airflow that's passing across the coil, the problems just start to multiply. And so the two biggest remedies for oversizing the air conditioner is variable speed and good airflow. You have to have good airflow and good mixing and all that other stuff to do it. So yeah, the new Manual S, there's options for people who want to size without heat pumps. Heat strips. If you don't want electric strips, there's options for that. So you can, and that's the advanced sizing criteria, where you size the heat pump to the heating load, and then you go and you look at the cooling load, and there's remedies to it being oversized. And then of course it depends on the climate too. You know, there's when we gave the talk at the symposium, Chris Hughes and Steve Rogers and I gave the talk. It was called something about the how to avoid the great heat pump revolt of 2027. And you know, the theory there being that if we don't do a good job at this, all the homeowners are going to get really upset, and then we're going to have a huge PR problem with heat pumps, and homeowners are going to throw their heat pumps out in their driveway and want their furnaces back. You know, and that's going to be the great heat pump revolt of 2027. So we're trying to avoid that, right? So we want, not only do we want it to be energy efficient, but we want the homeowners to be happy. We've got to have a good, you know, positive public relations campaign with heat pumps. And so, you know, the ability to do that well really hinges around good design. All the problems that you hear about heat pumps, they blow cold air, they freeze up. Those are not heat pump problems. Those are design problems. And we need to avoid, and they're avoidable. That's the good thing, is they're avoidable. And as you know, heat pump technology has come a long, long ways in just the last few years. So all the old heat pump issues that have we've heard about, especially in the cold climates, should not be as noticeable with the technology changes that we have.
Yeah, a couple things that back to a couple things that Ross mentioned. One of the distinctions that I think is really important to make whenever we're talking about this, and I probably should have made it right off the top, is new construction versus the retrofit market or the add-on replacement market. There is a huge difference between those two things, because and a lot of times when I go to conferences, especially if I'm talking to, architects, engineers, designers, all that, they want to have one conversation, which is about ideal situations, what you can build from scratch if you're able to control everything. But the bigger problem with heat pumps is the much larger market is the changeout market. And going in and changing a furnace with a heat pump is a risky proposition unless you are paying really close attention to the structure, the envelope, the insulation, the doors and windows, doing a blower door, these kind of things. Talk about that a little bit, Ross, because obviously you do a mix of both. You do new construction, but you also, it's right in the name of the show, right? You deal with old houses sometimes. That distinction, I think, often drives the decision making, right?
Yeah, totally. One thing to just add before I go there is that new construction is easy. It should be easy, right? You're building a house from scratch. You can do everything right from the get-go. It's an easy value proposition. You can go with heat pumps in any market. And it can be designed, sized right, and everything like that. You're still going to get it right. But when you're dealing with retrofit projects, existing housing stock, especially in a cold climate, or let's say in the New England market, there's some challenges there, right? So you could do a heat loss in a building, and 50% of the heat loss might be from infiltration. You might have a blower door on a regular house of, it could be, 15 ACH 50, it's crazy, off the charts air leakage. And it's because old houses, just weren't thinking about, air leakage, and weren't thinking about, the thermal envelope, and fuel was cheap. And so, as the climate is changing, as we get into these, heat pumps and applying them appropriately, as Russ was talking about, making sure we don't have this heat pump revolt, the unintended consequences are high here, in terms of if you think about applying a heat pump to an older building, there's a huge risk there if we don't think about all the other things like the air filtration and the heat loss in the building and running a load calc to be sure. And so in a lot of those retrofit projects, we almost always have an existing fuel source. And in most projects, that remains. So we may electrify that building and run the heat pump to provide all of the cooling, of course, and provide some of the heating. But we are going to have that backup fuel source of natural gas, and maybe propane, and maybe oil. But it's going to be there because it's already in the building in that case. And the heat loss might be 3x the cooling load, right? And the air leakage might be so surmountable that unless you're doing a whole house deep energy retrofit, you're just not going to solve it with heat pumps. You're not going to put in 6 heat pumps on the side of the building and go through an electric service upgrade to go from a 100 amp service to a 400 amp service, to make this all happen. There's so many challenges to electrify that type of building. And so, depending on the pathway, we think about pathways. What's the pathway that we're going to take with this project? Depending on budget, depending on climate, depending on existing building measurements in terms of blower doors, et cetera, we come up with what's going to be the most viable path. And unless you have a big budget and you're doing a whole deep energy retrofit, we call it, or, a whole overhaul, those are challenging to do. And so the fossil fuels typically stay there.
Yeah, I wanted to pull up this chart here. You see a lot of this kind of stuff about energy efficiency of heating systems, and you look at it's a little bit
it's misleading.
It's misleading, right? It's a little bit misleading, and this is something that you've looked at in the past and comparing. Talk about that a little bit. Why it's misleading? Because I'm also a fan of, and I brought up dual fuel at this conference that I did recently, and they looked at me like I had 3 heads and one of them was on fire, because they're thinking about new construction, right? Where you can design a new building to work with a heat pump and a heat pump alone. But when you already have a gas meter, and in many cases, even the way the power is being generated, we talk about places like Michigan or some places in the Midwest where power generation isn't necessarily that clean to begin with. Especially when we're talking about decarbonization efforts and all that, the going away wholesale from fossil fuels often doesn't make a lot of sense. So talk about that a little bit, if you would, Ross.
Yeah, I think there's heat pumps are really efficient, right? So we always talk about that. They are 200 to 500% efficient, depending on which brand we're talking about, what style of heat pump, et cetera, et cetera. And that's awesome. But that is misleading when you tell somebody that's non-technical that says, oh, this got a COP of 5, it's 500% efficient. I put $1 in, I get 5 energy units of energy out, thermal energy units out. The way that we like to look at it is in terms of like a levelized price per kilowatt hour. And what I'm trying to get to is basically the efficiency is one part of it, but the operational cost and the operational efficiency. And we try to put that on a level playing field. We call that a levelized price per kilowatt hour. And that's what we want to get at, because now you can say, I've got oil, I've got propane, I've got natural gas, I've got electricity with different types of heat pumps. Now I can put them on a level playing field and figure out what's going to be the most advantageous way to heat my building in this market. And it's based on the heat pump efficiency, but it's also based on the price per kilowatt hour that you pay. So if you're in an area that has a low kilowatt hour price for electricity, and you're putting in a heat pump, it's a no-brainer. It will win against any fossil fuel comparison. But if you're in a place like Massachusetts where we pay 32 cents a kilowatt hour, that's a different animal. And so you could, the rollout of these heat pumps, even if you designed and installed the best heat pump on the planet that we know of today, if the operating cost of that heat pump goes up compared to the natural gas furnace that they had in there previously, no matter what, even if you're doing a better comfort, the homeowner is not going to be happy with it. And so that is a concern, and that's in the back of my mind. So we want to make sure that we're rolling out these heat pumps properly from the proper design, proper application, but we also have to think about it in terms of what the actual operating cost is going to be. I'm all for lowering carbon. I'm all for electrifying buildings, but we got to do it in a smart way.
Yeah, and not bear the, a lot of times there's unintended consequences. This is something I talk about all the time. It's like, just because we know where we want to get doesn't mean that we're there right now either. And so, like I mentioned, you have some places where it's not like they're not using solar to generate this energy anyway. If you're in California and you have a very clean grid, and maybe your kilowatt hours for the electric utility are lower compared to the same, what you're paying per BTU on the fuel side, well, then maybe it does make more sense. But those are equations you have to do, right? And not just in terms of the actual energy cost, but also in terms of the carbon. If that's something you're also looking at, it's because it isn't one-to-one. It isn't the same everywhere you go.
That's right.
Do you have any thoughts on that?
We have this chart, the chart that's on the screen for anyone that's watching it. You've got a heat pump COPs across the top. So you can see COP 1, 2, 2.5, 3, and then obviously up to 5. So the one that's highlighted is 3, and it's coming down to 17 cents a kilowatt hour, and then it comes across. What that's telling you is that your price per kilowatt hour for using a heat pump that's COP of 2.5 with a price of electricity of 17 cents, it means that it's costing me 5 cents a kilowatt hour of thermal energy. So I'm paying 5 cents, 5.7 cents technically, to get 1 kilowatt hour of thermal energy out of that. And so if I were to put that and compare that to propane, fuel oil, and natural gas at different prices with a 90% or 95% efficient boiler or furnace, I can then put them on that level playing field. And so that's exactly what I'm talking about. So we have these charts, but we also have the other charts for the other fuels, even for wood and other, some of the Vermont and Maine market. They're a big wood and biomass market. So we have cords of wood and other things like that that are also in the chart.
Yeah, it's important to consider all these things, and ultimately the math isn't that hard to do so long as you have access to these charts. And that's so much of what we're saying is once as so many contractors and techs don't know, they don't think about this stuff, but once this is what you have to do in order to come up with the answer. It's not just a single simple answer.
Yep.
Any thoughts, Ross?
Yeah, I posted these on our website. I posted these on my Instagram page, etc. So if anybody, obviously wants them, we're happy to share them. So.
Yeah, it used to be such a simple equation, back when electric rates were just a flat rate. Now it's time of use, and that's just kind of thrown a real complex thing into the equation. You used to be able to say, well, on a BTU per BTU basis, electricity is 3 times more expensive than gas. Until we can be 300 or 3 times more efficient than gas, we can't compete. Well, now we can, but the equation's really complicated now, and it's gotten really strange. But something that I don't want to skip is my personal reason for wanting to electrify, and that's the whole safety reason. I've been doing design for 35 years, and since day one, it has dumbfounded me how it's okay for us to pipe an explosive gas into our homes, and then when we use that gas, it turns into a poisonous gas. and nobody bats an eye about that, And I've been in fights with builders where they wanted me to design where the furnace was inside the conditioned space, and I'd say no. First of all, code doesn't allow it, and second of all, it's a really horrible idea. I don't even like furnaces and water heaters being in garages because I've seen infiltration come into the homes from garages. So that's a whole nother thing. That's my personal reason. And of course we had the San Bruno pipe explosion, and I was actually driving home from a Christmas dinner from the company I used to work for. And there was about 50 fire trucks going down the road. And it was a family whose house blew up while they were getting ready for a Christmas party. And you just don't, you don't hear enough about that stuff. And so anyways, that's my little thing. That, that's totally aside from the dollar thing. There's even the software that you can buy to calculate these things. And we have not integrated that into our software yet, the cost effectiveness side of it. Even they have troubles with it because we simply don't know exactly when we're going to be using that electricity, and that can have a huge impact on the cost of it too. So it's always, your mileage may vary. You just have to put a big disclaimer on it.
Yeah, for sure. And you make a really good point about the time of use is huge, or load of use, periods of high load, how electric companies kind of have this very variable scale. And depending on where you are, you're going to see that more in some places than others, but it does make it a lot more tricky. Go ahead, Matt.
Yeah, I think my approach with homeowners when they've asked me about heat pump versus gas is just to kind of tell them what I know and then let them decide. Like, then to provide information, but not necessarily, try to make that decision for them, even though I might have a personal preference. Like, again, I like heat pumps. I think they're cool, I guess. I just think it's a cooler way to make heat, right? I just think they're fun. But it's like, that's my personal preference, and I'll provide information to people and then just try to let them decide. And I think that kind of gets you out of some of those, like you were saying, Ross, like just providing all the information, say, here's all the costs, like, this is what it's going to be. That way, when something happens down the road, it's not like you presented information in a way because you were really trying to like force, put your agenda onto somebody else, even though you might have a personal preference about it.
Yeah, I think the educational, awareness about what the homeowner, if they're going to be upgrading to heat pumps or whatever they're doing from an energy perspective, being aware of what they're doing and why they're doing it, and having, basically, like you said, describe all the pros and cons of these different systems and basically give it to the customer straight and let them make the decision, because there's no perfect solution. There's always pros and there's always cons to every decision. So it's just really a question of what's the right fit for that project. But I just know that in most of the projects in Massachusetts and Maine, we're in such a cold climate that, unless you're really tackling the air leakage of the building and insulating the building properly, just 50% air leakage and, R13 bat on the wall or plaster and lath, no insulation in the walls. That's a tough building to electrify with just heat pumps.
Yeah. And I actually think that's an important point about existing homes. The way I see existing homes is they're the classic low-hanging fruit. There is so much potential for improvement in existing homes. It's not even funny, and when I teach a heat pump class that's homeowner facing for one of the counties out here in California, I always tell them, always consider improving your house first. No matter what, that's always going to be a good thing. And then when I teach design classes, I'll tell people, don't design an HVAC system for a crappy house. And they're like, well, what do you mean by that? I go, well, if you design a HVAC system for a crappy house, it's going to be a crappy system because you're making up for the inadequacies of the house by oversizing the equipment. So always, reduce the load first and then put the heat pump on top of that. And then good things happen when you do that. That you can't go wrong with that.
That's a great point.
the analogy I always use is it's like you design a car with flat tires, and so you have to put a really big engine in it in order to compensate for the for the resistance of having all flat tires or all square wheels or whatever. You want to get the fundamentals straight before you choose the engine and the driver. One of the questions that popped up, not really a question, but a statement, is don't use AHRI data. So I wanted to let you kind of riff on that a little bit, Russ. Why don't we just use AHRI data when we're choosing equipment?
Yes, because we don't install heat pumps in a laboratory. That's the main reason. AHRI data is data from a heat pump that's in a very, very precisely controlled laboratory setting, okay, in conditions and assumptions. And we're not installing heat pumps in those situations, and so they're going to be precisely wrong instead of approximately right. So yeah, so you've got to look, and I always make a big point. There's nominal capacity, there's AHRI capacity, and then there's design capacity. And design capacity is, what is that heat pump going to do when it's installed at that house in those conditions? And that's always very, very different than AHRI. Unless I've been meaning to go through like the ASHRAE climate data and find a city that actually has the same conditions as AHRI data. And we should call those AHRI cities, where you could, so easy to size the equipment for those. You could just use AHRI data for
it. That's funny. Yeah, good point. I want to go ahead now and move into talking a little bit about some equipment specifics. So maybe some alternate technologies, but I'm just going to give a quick rundown of why, because a lot of people will say, okay, well, modern heat pumps aren't your granddaddy's heat pump. They're different than they used to be. And I just want to talk quickly about why that is, because there's a couple sort of fundamental reasons that they do operate differently. And I first want to talk about inverter-driven technology, because I think a lot of people misunderstand what's happening, which is that really what you're doing is when it gets real cold outside, you're spinning the compressor faster. That's what you're doing. And you can do that because now we have some of these technologies like vapor injection, so we can keep the compressor cool enough, or interstage cooling, whatever the case may be. There's a lot of different terms that people use for this in different parts of the industry. We use it in market refrigeration. We've had interstage cooled compressors for a long time in R22, where you're trying to get, do a lot more with a single refrigerant than you normally would be able to. And it really comes down to inverter technology and compressor technology. But the consequence is that it's not like you're getting that for free, right? Like, they still can provide capacity, but they're doing it by running the compressor at a higher RPM when you're talking about a variable speed compressor. And that is using more power to do that. It's just giving you the ability to still do that with compression refrigeration versus having to use something that's a little bit more objectionable, which would be like electric heat or potentially even fossil fuels. So that's one huge thing. Any thoughts on that as far as what you've seen on that side? Anybody here, including Matt? No. Okay, this is what I do. Sometimes I get like techie nerdy and then nobody wants to say anything. Okay, so I'll keep going. The next thing is, go ahead, Matt.
Could you speak a little bit to oh gosh, what is that? The mass, also that the mass flow rate, like that was.
Yeah. Kind of so, right. Because that's the thing, right? As your outdoor temperature decreases, when you're running a heat pump, your evaporator is now heat pump in heat mode. Your evaporator is now outdoors. And the colder it gets, the lower your suction saturation drops, the lower your suction pressure drops, right? I mean, that's how that works. And so your suction saturation, your suction pressure are always going to be lower than your outdoor temperature. So if it's -5 degrees outside, you're going to have an evaporator coil that's lower than that. And for anybody who works in refrigeration, you know the impact that this has because you're still rejecting heat to an indoor space that's hopefully about the same temperature as it was before, right? And what that results in is a much higher compression ratio. When you have a higher compression ratio, your output decreases. If in your granddaddy's heat pump, you just produced less heat as it got colder outside, as your compression ratio increased. One of the main reasons that is, to what Matt is saying, because your mass flow rate decreases. Your suction gas coming back to your compressor is lighter. If you have lower pressure, it's lighter gas coming back to the compressor. So every time that compressor spins or every time that piston pumps, it moves less because the mass is less. You're moving the same volume in the chamber, but the mass is less. So the way that these systems compensate for that, very similar to how ECM blower motors did when we were trying to get more airflow out of them, is that when you have situations where you're not getting as much, they just spin faster. And that's what we're doing. Once again, we're just spinning it faster. So now we can keep our capacity up, but you do that at a cost, meaning that it's going to draw more power the colder it gets outside still, because you're still fighting against this compression ratio problem. And I think that's just important to say, because it's not like when people look at a curve on some of these low ambient heat pumps, some of these hyperheat units, whatever, they're like, oh, look, even when it's 5 degrees, it produces the same capacity as it does when it's 43 degrees. Isn't that amazing? It's like, yes, but it's also drawing more energy when it's doing that. And that's not necessarily a bad thing, because you're going to do that one way or another, right? But don't get confused about what's happening. It is still using more energy in order to do that. It's just compensating for it by running a faster compressor speed. The other thing that I wanted to mention there is, and this we got some charts on that. I'm not going to dwell on that. Just kind of showing how you do have some pretty amazing abilities to continue to heat even down to low ambient conditions. But a lot of that is also due to, I thought I had a defrost slide here. A lot of that's also due to improved defrost strategies too, where we're really going to demand defrost nowadays, and more. And what that does is we only defrost when we need to. So only when the equipment is actually being impacted by ice buildup are we defrosting, versus doing an old school time and temperature method where you're kind of defrosting because you think you might need to, not because you necessarily know you do. And that also saves a lot of energy, because every time we're defrosting, we're taking that heat pump and we're slapping it back in cool mode to get the ice off, which is super inefficient way of doing that. But it's the only way that we have at our disposal on heat pumps.
Yeah, I think. No, go ahead, Russ.
I was going to say, and that brings up an interesting point too. Is one of the downsides to heat pumps is that their controls are so much more complicated than they used to be, and you really, some of the control strategies and the settings of the thermostats and settings of the lockout temperatures, and people just aren't getting that, and there needs to be a lot of education on that to make sure. I heard a funny story about it was one of the big heat pump manufacturers had a big problem when they first released one of their new brands, is that the manuals were in Japanese. And so they translated them into English, and there were some mistakes on how they did that. And so the people setting the thermostats and setting the settings weren't doing it correctly. And there was all these problems. They couldn't figure out what was going on. They finally narrowed it down to a translation issue in the manual. So, it's like how cars were, in the 70s, cars were simple beasts. You could sit inside the engine compartment and work on your car back in the 70s, and now you open the hood and it's like, it looks like a database. It's all wires and lights and stuff now. But we've gotten used to that, right? Car technicians have gotten used to it. The industry has changed, the industry has evolved, and I think we're kind of in that early part now where the industry still needs to do some evolving, but it will. I think we'll catch up. I'm pretty confident we will.
Yeah, the other thing to add with defrost is about baseband heaters. So that's a big difference between a cool climate heat pump and let's say a standard heat pump. Yeah. And so, for anyone, I guess, I don't know if everyone knows what that is. I don't know if you want to explain what it is, but
yeah, please do, for people who aren't used to it.
Yeah. So these cold climate heat pumps, one of the things that differentiates it from a standard heat pump is that when it does go into defrost, it's obviously switching to cooling mode for that time. And so it's actually extracting heat back from the building and sending it back to the infill coil, warming up that coil and trying to melt that ice. And that ice is going to shed off the coil in terms of water. But when you're 5 degrees outside or when you're 30 degrees outside, what the risk is that water comes down off of that coil and then it freezes in the cold pan that's underneath the outdoor unit. And we've seen many situations where a unit was installed in our climate without a baseband heater, and it's just it's not good. So what ends up happening is you fill the pan that's underneath the unit with ice, and the ice just continues to layer on top of layer on top of layer, and eventually it actually punctures the bottom of the coil, or bends the fins back, and eventually it will snap the coil or break the coil. And so then you have a massive issue in your hands now that you have a broken coil. And on top of that, now you have no heating in your building, or you're running on electric strip heat or on the dual fuel, fossil fuel backup. So yeah, basement heaters is a must-have in a cold climate when you're heating with heat pumps.
Yeah, absolutely. I wanted to go ahead, Matt.
And there's a few other things as well. I know that there's also, I'm not super familiar with them, but like wind baffles as well. And I know that those can actually, I think you can actually look at the specs and see how much, putting the wind baffle on will actually increase your BTU output and things like that. And then another one, even here, make sure you're not putting it right on the edge of a roof line where you're going to get like snow and water and stuff dripping off the roof onto the unit. Just be careful where you locate it.
Yeah, I mean, a couple of things to also add, especially in cold climate. So first is getting it on a stand. So you have to get it off the ground. So snow stands are huge in this market. So a lot of times they're 24-inch stands, sometimes 18, sometimes 36. So I need from a foot and a half to 3 feet off the ground. And the reason we mount it on the ground and not off the building, if it's by us, is because of vibration. So we don't want to, mount it to a 2x4 or 2x6 wood construction, because when it's in certain frequencies, you're going to feel that vibration inside the building. And a lot of those cantilevered, support systems that mount these inside the building, they don't have a wide enough arm. They don't get the unit far enough away from the building to meet the air intake clearances on the inbound side of the unit. So first thing is getting on the snow stand. Sometimes we have low ambient baffles, Matt, to your point, for low ambient cooling or for, wind protection. But a lot of times in a coastal environment or on the roof of a building, we worry about basically making a wind generator from the blade spinning back. So the heat pump fan motor is actually spinning backwards with the wind when the unit's off, and then all of a sudden it turns on to actually create a heat cycle. And when it does that, it's a tremendous amount of torque on the blower motor that it actually burns the motor out and turns the running. We also have surge suppression. So the other thing too is when we have these heat pumps turning on and off, and especially in our market where our electrical infrastructure grid is older, we are putting surge suppression devices on just about every single outdoor unit. You have a computer inside your heat pump that's running the heating and cooling with all the sensors and the controls. So you got to make sure you protect that. So sometimes we're just putting in surge suppression, sometimes we're going a step further with power condition. But the idea is just making sure we protect the heat pump just like we protect the computer.
Yeah, those are really good points. One of the things in our market, and this may be special to us with a newer grid, not necessarily, but with a very growing, where we're adding a lot of people to it, is the utilities keep jacking the voltage up. And so we're seeing voltages that actually exceed the rated voltage on the condensers periodically, and they will fail. We're seeing inverter failure happen massively in areas where the utilities are boosting up that voltage. So we use both a combination of, like you said, surge protection, but also using basically single phase monitoring. So we're actually doing voltage monitoring, but then often we're actually going in with a buck and boost transformer and intentionally reducing the incoming voltage to these units in order to prevent failures. And that has actually been very successful in cases where we have consistent overvoltage, which steady state overvoltage is not the same as a surge. A surge is, lightning strike, transient, something happens at the utility, you get these spikes that come down the line, you want to protect for that. But steady state overvoltage is also a challenge when you have all these electronics packed in. You have heat being generated, you have the potential for arc, and it definitely reduces failures there. Another thing that you mentioned that is very important to understand why in inverter-driven systems that are being used in low ambient conditions, because people always talk about, oh, man, this inverter system's so quiet. It's this thing's silent. Isn't that amazing? And when it's running in cool mode, it's super quiet. It's incredible. But when that sucker gets rolling, when it's really cold outside and it ramps way up, it's noisy. And the reason why is because that thing's running at a very high frequency.
150 hertz.
Yeah, right. I mean, you're running higher than, like you said, well over your normal electrical input frequency. And when that happens, you start resonating in places that you never did before. You're literally getting these resonant frequencies. So anytime you're attaching to the structure, you got to be really careful. But that's actually why when Carrier first came out with the Carrier Infinity, they shipped these suckers with these big old mufflers on them. And the guy's like, why are we putting a big old muffler in the suction line? Well, because it's not just a suction line, it's a vapor line, and it becomes the discharge line in heating mode. And when that compressor's spinning like a bandersnatch, I don't know if that's a real creature. I think that's a Lewis Carroll creature. But it's like a Jabberwocky, you know, it's fictional. When that thing's really spinning, you really have to be careful about noise. And that's why they would ship those mufflers for that purpose.
Mm-hmm.
All kinds of weird
noises. The fan motor also creates a tremendous amount of, I call it like waffling effect, where it's literally, as it's cycling on, it's almost trying to pull and push against the building. So it's creating this waffling effect. So when it cranks up, not only the compressor cranking up, but the fan motor cranking up. If you don't have, a lot of those stands are only going to be 12 inches, maybe 15, 16 inches long. So you're only going to have maybe 4 inches on the intake side, on the intake side for the outdoor unit to let air in. And it's just not enough. A lot of those manufacturers need 8 inches or 12 inches on the intake side. Yeah. So it makes a tremendous difference if you can get that unit further off. So we just ground mount it. That's just our thing. Ground mount meaning on a stand. Yeah. That way the vibration gets lagged into the ground, and dissipated that way.
I want to get to a couple of these questions or statements. Jennifer also said you can often hear the reversing valve slam as well. That's another thing. A lot of manufacturers do allow for like a quiet shift mode, but there is there's expense there where you have a time delay. Basically, it shuts off and allows it to equalize a little bit, then it shifts. And so there is a little bit of a, in order to not have, Mrs. Johnson call you about the crazy noise. It does have a little bit of a capacity decrease that you see, but especially in cases where that condenser is going to be heard, it's outside of a window or something like that. Then that's a really good mode to deploy where you have that option. Another thing that I wanted to point out, and this was Jim Foltz when we were showing that picture of of defrost. That specifically was the Copeland White Rogers board that we showed there. And so but one of the things that I want to mention here is that you can often nowadays control a set temperature for auxiliary heat. And that's another way to get a little bit of extra capacity. So that way you're not bringing on auxiliary heat unless you absolutely have to. Sometimes it's in the thermostat. You can control that based on, localized weather data. Sometimes it's using an outdoor sensor. But a lot of times your more advanced aftermarket defrost controls or even factory ones will allow you to set that up as well, which is another nice kind of energy saving feature. I wanted to get, yeah, go ahead, Matt.
Well, this kind of relates to the duct systems as well, but Ross, what types of indoor units are you guys typically pairing with these outdoor units?
So on most of our, I'll call it VRF, mini split type jobs, almost all of them are ducted products. There are of course some, unique applications or installations where we have to go a ceiling cassette or wall mount or something that's ductless, but the majority of the products that we do are going to be ducted. That's just the way we like to apply them. There's a bunch of advantages to it, of course, disadvantages too, but we find that to be the most successful way to, obviously in a retrofit project, you have ductwork. So a lot of times we're trying to utilize that ductwork. We might set up a true flow and just make sure that we have, proper airflow, measure the set of pressure, just make sure that we're good on that side. But ultimately, we just want to make sure that we can move the proper airflow once we've done our JDS, just make sure we're going to be good there. But yeah, we could just be more targeted with it.
I wanted to spit this one out to Russ. One of the things that Jack Rise used to always say, number one rule with any system is don't blow air on people, which solves a lot of the problems. If you design a duct system where you're blowing air on people, that's a big deal. But on heat pumps, proper airflow and proper charge are huge. Talk a little bit about the airflow side. Sure.
You can look right in the expanded data tables. Not so much on the heating side. It's kind of weird, but definitely on the cooling side. Capacity drops when airflow drops across the coil. You can see it right in the tables. And another interesting thing too is SEER gets worse too. So when you reduce airflow, it's a double whammy. You lose capacity and you lose efficiency. And so that's one reason to have good airflow. But the other one is mixing. I can't emphasize that enough. Everyone talks about, oh, hot air rises. It's always hot upstairs. It's cold downstairs. And the reason hot air rises is because you have a difference in temperature. If you can avoid that difference in temperature by mixing the air as quickly as possible, you don't have stratification. And so good register selection, good airflow, good, all the manual T stuff. And then the other thing that's kind of interesting is that heat pumps don't blow as hot of air. And that, in a way, that's a good thing, because when you're blowing super hot air into a cold room, you've created two sections of air and they're going to want to separate. But when you're blowing air into the space that's closer to the room temperature, it's already done some of the mixing. There's less mixing that needs to be done. So that should actually improve things. You should have less stratification. And then, of course, that's all dependent upon equipment sizing. If you oversize the equipment, you're going to have short cycling, and it's going to run for a short period of time, and then it's going to stop, and then the air is going to separate. It's going to stratify. But the longer those cycles run, the better mixing you have. It gives more time for the air to circulate through the entire system several times. So I can't emphasize enough the whole airflow issue. I go into a lot of detail in our classes that we teach. So yeah.
What you just said is exactly what I talk about all the time in terms of set maximum heating airflow. A lot of times there's a option for you to set what they call comfort. And what that is reducing the airflow over the indoor coil in heat mode in order to make the air warmer. So that way, when Mrs. Johnson feels, okay, that feels a little warmer, that's a little better, right? But what happens when you do that? Well, literally what you're doing is you're driving up your head pressure. That's what you're doing. That's what you do when you run lower airflow over your condenser. And now your condenser is the indoor coil. You're driving up your head pressure, which does what to your compression ratio? Increases it. What happens when you increase your compression ratio? Less capacity, less efficiency. So the easiest, simplest, most magical way to get more capacity and efficiency out of a heat pump is to run really good airflow over both of your coils, which means efficient use of defrost, and nothing impeding anything, no dirty filters, no bushes clogging up the outdoor unit, no snow on it or anything like that, and running high airflow, as high as you possibly can on the inside. And the thing that drives me nuts is people are like, well, the air is colder when you run more over it. Well, it's lower temperature, but there's actually more heat contained in it. And the other effect is you also get less duct losses. Right. So when you do have ducts that are in unconditioned spaces, which they often are in a lot of markets, you also get less duct losses when you aren't artificially driving up the air temperature for no reason. And so if we're not blowing air on people and we're designing our register strategies and all that properly, and if the customer is educated that it's okay if it blows on you and it feels a little cool, that doesn't mean it's not heating your house. We can actually get a lot more capacity and efficiency out of these air source systems.
Yeah, I like to remind people that you can heat a 70-degree house with 71-degree air, right?
Right.
Because it has more BTUs in it than the air that's in there. Of course, we don't want to blow 71-degree air on people. They'll think it's freezing cold. And obviously, we all know that air feels colder when it's lower than our body temperature and it's blowing across us. We feel that heat leaving our body. So even though we're heating the space with air, if it's lower than our body temperature, it's going to feel cold, but the space is actually getting warmer. So it's kind of it's definitely a don't blow air on people if you can. And that's the whole reason ceiling fans work, right? The moving air feels colder than still air. So yeah, we're gonna have to pay a lot more attention to register selection and placement and all that good stuff.
Yeah.
Yeah, we usually try to sell it to our customers and clients that these heat pumps work low and slow, right? And that you want them to work low and slow, and you just want to match up the heat loss, to keep up the heat loss in the building. So as the building loses some BTUs, you're giving the building that BTU. And so two of the things that we get from complaints that people don't understand is, one, the heat pump's been running for a long time. Is that a good thing? I feel like something's wrong, and because they're used to a furnace or a steam boiler that's on, off all the time, cranking and shuts off. And so there's definitely a mental part of that as far as getting used to the heat pump running for a long period of time. Like I talk about cruise control is the way I describe it. You want your car to be in cruise control when you're driving on the highway. Let it as you go up a hill, let it adjust for the hill. And as you go down a hill, let it adjust for that hill. Just let it be in that kind of good sweet spot. And the other thing too is like you guys both talked about, which is if they put their hand on the register, it feels cooler than what they're used to as far as blowing on the registers. And so if they're used to an 80% gas furnace that's blowing 160 degree supply airs at them, that's a little bit different than 100 degree supply air coming off from the heat pump. So there's definitely, those are the two, maybe concerns that we may get or feedback that we get. But once they understand it, then they get it, and if our duct design is proper, then we're not blowing on people, so they're not going to feel it, and so you won't get that complaint or you get that concern.
Let's take a last few minutes we have here. I also have a question from Sophie that I want to try to get to right at the end, but let's talk about some of the future ideas, but also some of the other ways that we can use heat pump technology that's not our typical air source heat pumps. Obviously, we have a couple geothermal type of structures here from a recent 3D video that I did. But Ross, do you run into many non-air source heat pumps in your market, or are you able to spec any?
Yeah. We do a lot of geothermal design. Obviously, for the people that are up, kind of on semantics, I always say, no, it's a ground source heat pump design, just so that, the haters aren't saying it's not geothermal. But anyway,
right.
But ground source heat pump, geothermal, yeah, absolutely design it. Most of the stuff we do is vertical closed loop borehole designs. So I think it was the previous picture that you had up. Yeah. Oh, actually, no, that's just the open, pump system. But yeah, the vertical closed loop, there it is, kind of, on the left-hand side. We do that on a lot of projects. They're more in the high-end residential market because it does have a capital cost up front. But hey, if you're tapping into 50-degree temperatures where we live, that's a lot better than 0 degrees or 5 degrees, And so if I have to take if I can use that 50-degree heat source that's in the ground inherently, and I'm trying to keep my building at 70 degrees, my delta T is only 20 degrees. I only have to boost it from 50 to 70. The heat pump can do that really easily. But if, as opposed to air source, I got to bring it from 5 degrees up to 70, right? So the delta T is much wider in that arrangement. So we love ground source heat pumps. We love geothermal. Obviously you need proper design, proper application, but when it's done right, it works phenomenally well. No defrost, no outdoor equipment, no effect from salt air or excessive breezes or anything like that.
Yeah, I love it. And then, I always have to put my, mine and Michael Hausch's crazy thing here. But I think if we wanted to have the world's perfect setup, we wouldn't even have this outdoor air source unit. We would have a combination of ground loop and this indoor sort of hot, cold buffer tank, domestic hot water, sort of the magic box design. And one of the big things that this solves for, because when people see this, they're like, I don't get it. I don't know why. One of the big things it solves for is that you can do simultaneous cooling and heating. So now this system becomes a dehumidifier as well. And not just a dehumidifier that, because a lot of dehumidifiers, when you install them, it's blowing warm air, like it's higher temperature air that you're blowing. You could actually, by using mixing valves and other things, you could control that. So you're literally dehumidifying and blowing back in lower humidity at essentially the same temperature as your indoor air. Which would be super powerful, get better mixing, especially for low load homes. But then you also have the benefit of not having to rely on peak periods of consumption. You could basically produce cooling at a much lower rate, cooling and heating at a much lower rate constantly with a smaller unit. And of course, my favorite part is if you can make a design where you're using R290 propane as the refrigerant and keep it all outside. Now you de-risk it from a safety standpoint. And you are able to use one of the best refrigerants out there and instead use secondary fluid inside the structure. So I don't know, Russ, have I ever pitched this? Have I ever given you the whole spiel on this? No, you haven't heard it before?
I'd love to hear about it sometime.
Yeah. Okay. Well, I mean, that's what I'm doing right now, but I'm kind of dropping on it all at once. Ross, I know I've kind of annoyed him about it before. What are your thoughts on this kind of future, Ross?
So what you've just described, for the most part, we're designing right now. So we're not using R290, we're using, in some cases R32, some cases we're using R410A, in some cases 454B. My goal would be to get to 290. We're not there yet, obviously, from a product perspective, but the ability to use hydronics in the building, to heat and cool the building, that's my background. That's what I was taught in. That's what I learned from, soldering pipes when I was 5 and 6 years old, right? So it's the way that, I think a building should be heated and cooled. You know, we have the B2 battery concept, store that energy in tanks. We can get into phase change material to get more BTU extraction and storage. We can get through coast modes where we have peak, time of use rates that are much higher. We can do simultaneous heating and cooling with these systems, like you said. So we could literally be heating the basement at the same time that we're cooling the loft. We can move BTUs from one system to the other. We can move it to outside if it's more advantageous to go outside, or we can reject to the ground with a geo system if it's more advantageous to do that. So, it gives us the kind of ultimate flexibility. If a house wants radiant floor heat, we can do that with this system. If they want to run dehumidification, we can do that with the system. And hot water, chill water systems are not new, right? Hot water, chill water is a lot of how high-rise, construction is built, with a 4-pipe system, hot water off the boiler plant, and chillers that are doing the chill water side of it. So using hydronics is nothing new here. It's much of how Europe is heated, of course. And so now, like you said, if I can do a self-contained box that's outside that has a really great refrigerant in it, I don't have to worry about the refrigerant phase outs in the future. I don't have to worry about changing my 410A line sets when R32 and other, other refrigerants come down the line. I can have it all self-contained in one box outside. I just take that box off, put a new box back in, reconnect it back up, and all of the indoor stuff, the piping, the ductwork can stay the same. So you get inherently you have future proofing with this type of system as well. So we're designing systems with this right now.
Yeah, and this can work with radiators. You could even do radiant cooling with this type of system if you used mixing, so that way you could actually keep it to a point that you're not hitting dew point in cases where that's advantageous. There's lots of things you can do. You can do floor heating. I mean, you can go on and on and on and on. I'm actually going to build one of these. This is my little secret. Using basically Yetis of hot tub and cold plunge, and using that kind of as obviously I'm not using it at potable water, but these super insulated. And so now you have the advantage of, hey, if I want to hop in the cold plunge, I've got that, but it's also still a BTU battery. Now, it's idealistic. It's me just playing around and being silly, not mass market stuff. But this really is, I think, a huge opportunity for our industry, and probably where we're going to head. And again, what I'm showing here is just an example. It's just a prototype. A lot of it will probably start in structures that already have maybe radiator setups and that kind of thing, or markets that makes more sense. But I do think it's coming and has a huge future, especially as we deal with a lot of the refrigerant stuff where we're really all getting sick of having to keep changing. And once we get to where we're using natural CO2, propane, and in some cases ammonia, I think we're going to be a much more stable and kind of future-proof designs.
Yeah, we did a segment on Future House on for part of the Ask This House. It was probably 6 or 7 years ago at this point, so it's definitely a little bit outdated. But it's 2 buried tanks in ground, well insulated, one hot, one cold, running off an air-to-water heat pump, and be able to switch it back and forth between heating and cooling, doing that concept. So that's on YouTube and out there. But yeah, just to get a feel for what that installation might look like.
Yeah, there's a show called This Old House, if anybody's heard of it. They do a few things now and again, and Ross is involved with that. So, go look them up. They've got a little YouTube channel out there. Good stuff. I wanted to finish with Sophie. I'm a big fan of Sophie. So she said, do you all set auxiliary heat based on balance point from the load calc or temp lag at control? How much do you explain to the homeowner? So I'll kind of start with my take on this, which is we can get really complicated, but the reality is that when temperature starts to slip, the homeowner gets unhappy. And so allowing the thermostat to largely do what it does with just kind of setting some very practical outdoor temperature limits. We don't have to get down to the exact number, but really all you're preventing is when the homeowner does the smash it up, smash it down, they're trying to do some sort of setback strategy. If they would just leave it be, then the thermostat lag would really dictate when your heat strips need to come on. When it starts to slip by 2 or 3 degrees, the client's not going to be happy unless they start to get a little additional heat in there, which is why, and this is sort of your traditional, heat pump setup where you have auxiliary heat in place. But what you're really trying to keep is just if that client comes in and they let it get real cold in the house and then they smash it up, you don't want the heat strips to come on just in those sort of situations. Anybody else have any other thoughts there?
Yeah. Oh, go ahead, Russ.
I was just going to say, I kind of like the idea of an outdoor temperature sensor, and that kind of strategy. The problem with the balance point is, as much as I say good things about load calculations, they're not perfect. So I wouldn't base it on that until you've had a couple years of actual use patterns to validate your loads, I guess. Yeah, just using the outdoor temperature. And then you can take into consideration economic balance points too. So you can get really, really complicated with that topic. But yeah, I would say probably the outdoor temperature sensor is probably one of the best ways to go.
Big difference if you're talking about natural gas or propane as being, that's a very different thing. And so when you're talking about a dual fuel strategy, that's when getting really detailed on the economic side makes a lot of sense. Yep. But when you're talking about electric heat, electric heat isn't that much heat anyway, in most cases. Like you get 5-10 kilowatts. I mean, I hear some people who will have more in some markets, but at that point, it's like you're kind of defeating the whole purpose. You're not getting that much heat out of those as it is. And so you're really just trying to prevent it from slipping too much. And obviously it's there for defrost as well. That's another time when it makes a lot of sense.
Yeah, I was going to say, it depends on what kind of system we have, for what aux heat we have. If it's natural gas, we might be actually setting an outdoor temperature because we're concerned about the economic balance point, and it's more cost effective to run the natural gas than run the heat pump. But if we're talking about electric strip heat, that's a completely different situation. In that situation, we may be just based on time and temperature, based on the thermostat, where the heat pump is the first stage of heat, and it's going to try to do its thing. And if it can't keep temperature in the condition, we're still going to let it run, and we bring on the electric strip heat as backup. And so in that situation, it's almost always more advantageous to let the heat pump try to heat the building than run the strip heat. Even when it's 5 degrees outside, we might have a 1.75 COP. It's still better than 1 or 0.95.
Right.
So the heat pump is still going to be more advantageous there. So we think of it as a covalent system versus a bivalent system.
Right.
And with covalent systems, of course, we're letting the heat pump run, and then we're bringing the strip heat if it struggles to keep up.
Yeah, it's so funny when I'm answering questions like this, because I as much as I try to not answer from my own Central Florida experience, it still slips out. It's like I'm still just like, because people talk about like emergency heat. It's like, well, when do I switch to emergency heat? It's like never. That never makes it doesn't matter if your heat pump is producing a COP of under 1, like it's still producing heat. So if you shut it off, you're still reducing the amount of heat that you're producing unless your backup heat is designed to where it can handle it all. And that's what a dual fuel or a hybrid heat system is designed for. And then of course, yes, then that makes sense. And so it really just depends on what you're talking about. Her specific question was about electric heat and when it should come on. And that's a fairly simple one. But when you're talking about dual fuel, it definitely matters. Like all the stuff we were talking about, doing the actual calculations, looking at the expense and all of that factors into it. All right, we are already well over, so I want to thank you guys. It's been a really great conversation. It's always fun. Russ, first time having both of you guys on here, and it's a joy as always. And everybody who participated, we had a nice, consistent audience the whole time, even late at night here on the East Coast. Always appreciated, and I look forward to hanging out with you guys again sometime.
Cool. Thank you.
Thank you guys.